Okay, so first, quick announcement about the calendar. Let's see, today is class 27. We're going to talk about series and in particular geometric series. This word series is going to appear for many, many, many classes in a row. So this is just our intro to series, our first of many days on series. Also, project number 7 is officially assigned. It's on the tables. Make sure you have one. It's not due until April 24, which is, I think, a week from Wednesday. No. Is that right? Friday. Why are we having trouble here? 24, a week from Friday. A week from Friday is when this project is due. Is that right? Yeah. So yeah, this coming Friday is staff development day, so employees come in, but students don't. And then Monday is Patriots Day, so we're closed on Monday. All right. One more thing while we're thinking about the calendar, this coming Wednesday at 3 o'clock in the afternoon, raise your hand if you don't have class Wednesdays at 3. I think a bunch of people are in statics afterwards. Okay, so if you aren't in statics, then there's a presentation by a famous author. Her name is Deva Sobel, and she wrote a book that I think was fantastic called Longitude. It was called Latitude. I forget which word it is. But the book was great. The book was really good. She's a science writer, and she's going to talk about her experiences as a science writer. So that's at 3 o'clock Wednesday coming up. I'll remind you again on Wednesday. It's in the library. But anyway, I'll say that we don't get very many mathy, sciencey speakers here at GCC, so I'm going out of my way to mention this one. All right. Any questions on anything before we jump in? Typically they go less than an hour. Yeah, but certainly you could leave if you needed to. Yeah. All right, top of page 11. Let's see. In this class, we learn about series of numbers. So number 1, a series is the sum of a sequence of numbers. We talked about sequences last class. Remember, a sequence is just a list of numbers. A series is where you add up a list of numbers. So for example, 1, comma, a half, comma, a third, comma, a quarter, just a listing of numbers. That is a sequence. But if we decide we are going to add them up, 1 plus a half plus a third plus a quarter forever, then that is called the corresponding series. Understand the difference between sequences and series? What do you think you get if you add up 1 plus a half plus a third plus a quarter forever? 2, 1.9. Infinity. E.
Well, I know
why not?
Half plus a quarter plus by 8.
Okay, so Alex's theorem is that 1 plus a half plus a quarter plus forever somehow is equal to 2. So 4 it says close to but not equal to 2, like it's going to be less than 2. All right, so we got to, like it's not even clear what it means to add up infinitely many positive numbers. So we got to start there. So number 2, just some more vocabulary. So the individual numbers are called the terms in the series, and we're going to try to define the sum of an infinite series, which is tricky, right? And this is the issue we're running into. So here's our definition. You have this infinite series, sum of S sub n, and so that just represents, remember, we've seen sigma notation a bunch now, so this is just S1 plus S2 plus S3 plus forever, right? Starting at n equals 1 and going forever. So here's what we're going to do. I don't know how to add infinitely many numbers. I do know how to add finitely many numbers. So we're just going to look at S1 by itself, then we're going to look at S1 plus S2, then we're going to look at S1 plus S2 plus S3, all of which we can do, right? And we can look at the first billion of these partial sums, they're called. So now I have a sequence of numbers. S1 is the first number in my new sequence. S1 plus S2 is the second number in my sequence. That's another number. That's the third one in my sequence. That's the fourth one in my sequence. And now I have a listing of numbers, yes? And these are called the partial sums, because you are adding up partially many of this infinitely many termed series. And so it says if this sequence right here of partial sums converges to some number s, where s is a finite number, then we say that the sum of the infinite series is actually equal to s. And we say that the series converges to s. So let's just look at a quick example. We'll do Alex's example up here. Well, I'm really reluctant to say that on record here, but let's see what happens here. All right, here we go. So the very first term in Alex's series is 1. So that's the first number in our new sequence. The next term is going to be 1 plus, what is happening here? First term is 1. Next term is 1 plus 1/2, just as a number. And the next term is what? 1 plus 1/2 plus quarter. So 1.75, and then we'll do one more out here. I'll just take the previous answer and add what number? 1/8. And so this is now, if you just look at the right-hand column, this is a sequence of numbers, right? And we're not frightened by sequences. Those are just lists. Adding infinitely many things is frightening, but we are giving meaning to that frightening thing. Let's just do a few more here, see if what Alex suggests is reasonable. So next thing we're adding is what? 1/16, and then we're going to add 1 over 32, and we're going to add 1 divided by 64, 1 divided by, what, 128? How many, what do we think? Are we convinced? Anybody play the game 2048? Don't look at it. It's so addictive. Okay, so what do we think of this sequence of numbers? Do you buy that that sequence looks like it's converging to the number 2? And so again, taking away the frightening part, which is adding infinitely many numbers, but rather just looking at a list of numbers, which I can just look at and think about what this thing does forever. Oh yeah, seems like that sequence of numbers, the list of numbers, converges to 2. And so we will define this infinite sum that Alex has proposed here, 1 plus 1/2 plus 1/4 forever. We're going to say that that thing equals 2. And Sephora was absolutely right when she said it never gets there, right? We are never going to get to 2.01 or 2 exactly, but that's okay. We just need to say in the forever part, does it get as close as we could possibly hope to 2? Yes, it does. So that's what we define the sum of the series to be. All right, so it never gets there, but it gets as close as we could hope. Like you could say, I want it to be within 0.00001 of the number 2, and we can go far enough out and we can get there, and you can change your mind and say, no, I want to be even closer, and we can get there. Okay, number 4. Let's go to Dean. Okay, so we're going to use the calculator to help us, and then we're going to write down some stuff which will lead to a formula. So calculator first. All right, so the first 100 milligrams, so we'll just type in 100. So this is what we have initially. And then 24 hours later, how do I figure out how much caffeine is going to be in my body? Levi. Let's see, multiply by 0.06, right? Because the 6% is still in the body. So multiply by 0.06. And then you said add. Because 24 hours from now, I'm going to drink my next cup of coffee. So, okay, 106. And then, is that okay? And then I'm going to take 6% of this number and add another 100. But it's really great the way Levi gave that to us, because if I just hit enter right now, the calculator is going to repeat this calculation, which says take the previous answer and multiply by 0.06 and add 100. So here's the new previous answer. So this is exactly what we want. So it's 106.36. That's at the start. That's right after the third cup of coffee. And then right after the fourth and the fifth and the sixth and the seventh. So this is the answer to the problem. It's that crazy decimal. But does it appear that we're kind of honing in on something? Just looking at the number of digits here, we've been at 106 point the whole time. And 106.3, the 8 is now consistent. The 2, 9, and 7 are repeated in these last two. So it feels like we're kind of leveling off someplace, just like we could maybe think of leveling off at 2 for Alex's theorem. Okay, but what if we don't have the calculator? What if we wanted to know really mathematically what's going on here? What is that number and why are we approaching it in the long run? Okay, so here's what we're going to do instead. We're going to say that, let's see, so this, I don't have good notation here. How about S sub 0 is the 100 milligrams that I have right at the start of that very first day. And then S sub 1 is going to be 24 hours, 1 day later. And so we'll write down exactly what Levi had said. He said, take the previous answer, multiply it by 0.06, and then add 100, yeah? Okay. And if we do it one more time, maybe we'll start to see a pattern pop out. So Levi would say, take the previous answer, which is that answer, multiply it by all 0.06, and then add another 100. So I'm going to put the plus 100 here at the end. And I'm going to multiply 0.06 by both of these terms, and I'm going to distribute that 0.06. So this first guy becomes 100 times 0.06 squared, and you multiply the first one by 0.06, and then the next one also by 0.06, plus 100 times 0.06. And then the last plus 100 is the new cup of coffee we just drank. So we said a lot, but wrote little. Questions on where that comes from? And we'll do one more here. That's 4 equals. So again, distributing a 0.06 into everybody, because it's 0.06 times the previous day. First term becomes 100 times 0.06 to the 3. And then, yeah, oh, sorry, made a mistake there. S3 is what I meant. Yeah, not one less, the power is the same. Okay, so then this next guy right here, we multiply it by 0.06 and it becomes 100 times 0.06 squared. And then we'll multiply this guy times 0.06 and we get 100 times 0.06. So that's 6% of the previous answer. And then at the end, we have our fix and we add 100. Okay. Okay, so without hitting enter, 6 or 7 times on the calculator, we could just now zip to the answer that is S7, I think, right? 100 times 0.06 to the 7 plus 100 times 0.06 to the 6. So we could just write the pattern out. That would be fine. But like I said, we kind of want a sense of what's going on in the long run and can I predict, that messy decimal that we got there. So number 5, we're going to leave blank for a moment and we're going to fill in with a little theory and then we'll use our formula. Okay, number 6, let's go to Alex. Okay, so I've written in red here some stuff underneath the last thing that we wrote up above. And so A is 100 for us, and then A times X is 100 times 0.06, and then AX squared is 100.06 squared. So how much is A? 100. It's the first term, but you got to be careful about the word first. It's the guy that hasn't been multiplied by anything. It happened to be the last thing we wrote. And how much is X, which is the multiplier that you get from one term to the next? Is 0.06, right? Every time to get to the next term in this list, you're multiplying by another 0.06. Okay, so for us, we had A was 100 and X was 0.06. Okay, so again, it's called a geometric series if you keep multiplying by the same number every time. So you can have a finite geometric series. And so what this says here is that S sub n minus 1 is equal to that stuff. Let's make sure we buy that. When we had S sub 3, what was the highest power? It's 3. And so whatever the little subscript is, it's n minus 1, had better match that highest power over there. Okay, fair enough. Why is it an n minus 1? That's really kind of an arbitrary choice to make the formula in the next line look a little bit nicer. The fact is I can never remember that formula anyway, so I'll show you how I figure it out. But here's the formula. S sub n minus 1 is equal to a times 1 minus x to the n, all divided by 1 minus x. Let's use the formula, and then we'll figure out where it comes from. So let's do this for our example up above. So A is the leading term. What is it? 100. And then it says 1 minus x is 0.06. Okay, so here's the tricky part. N. It says you raise it to the n, but you got to recognize that they are calling in this formula that thing n minus 1. So S7 is what we were after. So how much is n? 6 or 8? It's 8. Yeah? Right? N minus 1 is supposed to be 7. So apparently n is 8 in our example. Okay, so then what we're supposed to do here is raise the x to the nth power, which is 8. So we raise it to the 8th power, one more. That's the part that I remember, by the way. I can never tell the n minus 1 from the n, but I just know I'm supposed to raise it to the power that's one more. And then that's divided by 1 minus how much? 0.06. So this is what we're going to type in. And let's see what we get. Okay, so what do we have here? 100 parentheses 1 minus 0.06 to the 8. And then that gets divided by, oops. And that gets divided by 1 minus 0.06, so 0.94. Kind of hoping they'd be exactly the same, but we're off by, 3 whatever's there.
Hold on, this is the definite number it's supposed to be.
That's the answer it's supposed to be. Was I supposed to? No, this is the finite answer. This is not the forever answer. This is the finite answer. Is it possible I shortchanged the number of enters here by 1? Maybe I missed one. Let's try again. So what did we say? We said we're going to multiply that by 0.06 and then add 100. Okay, so I'm just looking for this 87 at the end here. Okay, I think I just missed it. I just shortchanged it by 1. Yeah. Okay, so that's our answer, and it's kind of nice because if I wanted the 1000th one, doing it Levi's way, no offense, Levi's way is fantastic, I would have to hit enter 1,000 times, right? But using the formula, you just type in one simple calculation. So the formula is a good thing. Okay, but like I said, I can never remember the formula, so here's what I do instead. Okay, so let's take a look at the original list, which I'll say is a plus ax squared plus dot 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 plus ax to the, all right, so I'll go out to n minus 1. That's what our formula is going to get to. So this is just our definition for the sum going out to the n minus 1 power. And then what we're going to do is we're going to multiply everything here by x, which is that common ratio. It was like multiplying by 0.06 in our example up above. So multiply both sides of this equation by x. So we go x times Sn minus 1 equals, and then we're going to multiply every one of these guys here by x. So this first one times x is ax, plus the next one times x, ax squared, plus ax cubed, plus dot dot dot, plus, I'm going to write down the last 2 guys. So what's the last 1 guy? To the n, right, if we multiply that by an x. So then what was the previous to last guy? N minus 1. And then we're going to subtract. All of this is to try to prove that wacky formula that just came out of nowhere. We're going to subtract these 2 things right here. On the left-hand side, just write down Sn minus 1 minus x Sn minus 1, just subtracting. At the right-hand side, something good happens. Lots of good things happen. You see all the canceling that's going to happen? We're just subtracting the top thing from minus the bottom thing. So does this A cancel with anybody? No. Okay, so A is left over. What about the AX on top? When I subtract, it disappears, yeah? And the AX squared disappears. And they're all off by 1, right? So the first guy is still going to be there, and the last guy is still going to be there. So when I subtract over here, these two will cancel, but then there's nothing here to subtract. So what's the sign? It's a minus. So buy this? Because there was nothing to cancel. So the AX cancels when you subtract there, right? That cancels, but the A is without a partner. First guy and last guy don't have partners, but everybody else cancels. What's that? Nothing wrong with being, there's no judgment against being single. But those are the people without partners. Okay, on the left-hand side, we can factor out, yeah? Sn minus 1 comes out, what's left? 1 minus x, this is starting to look familiar. There's a 1 minus x in our formula. What can you factor on the right-hand side? A comes out, what's left? 1 minus x to the n. A. Divide by 1 minus x, not a mystery. Okay, so the only thing I'll say to you is that because there's this n minus 1 in the formula and another power is n, it's just really important for you to make sure you are clear. What am I plugging in here? Is it n? Is it n minus 1? Is it n plus 1? Just take your time on that. Right? You'll have the formula in front of you on any homework or test, but take your time. Okay, next page. Number 8. Let's go to Sam. A lot is correct. All right, so let's just start listing out here how many pennies are on each square. So the first square we said has 1 penny. Second square has 2. Next one, 4. Next one, 8. We got to figure out what's going on in the last square. Seems like 2 to the 64 is reasonable. Is that right? This is like just thinking about the fourth term, it's really 2 to the third power. Yeah. So it seems like the thing in black there is 1 more than the power. So over here, 2 to the 63rd. Okay. All right. So adding that up with the calculator involves punching in 64 things. I don't want to do that. But this is our formula, right? This is a geometric series. What's the constant multiplier? 2, right? Every term is double the previous term. Fantastic. So let's use our formula. So the formula says S sub, okay. So again, I got to be really careful here. I don't know what to put. I mean, I feel like I'm putting the 64th term. Is that fair? We've got 64 terms here. So I think I want to put 64 right there. And so the formula, I'll just put it over here on the side again. A1 minus x to the n. This is the tricky part, divided by 1 minus x. So I'm going to fill in everything except the tricky part, and then we'll fill it in. How much is a? First term? First term in red is 1. And then times 1 minus, what's the x? Is the constant multiplier. That's a 2. I'm going to put a little blank up here. We got to fill that in with the power. Divided by, what goes downstairs? 1 minus 2, the same 2. Okay, so here's all I know about that formula. Whatever this little subscript is here, that's 64. The power is always 1 more, 1 greater. That's what it is. I can't remember n minus 1 and n plus 1. I can just remember that power is supposed to be 1 more than this guy. So what? You could do that. Ultimately, we just need to get to the place where we're putting a 65 there. And this is something we can type into the calculator. All right, so can somebody type that in for us? Anybody have a number?
68.
3.68 times 10 to the 19. Okay, that's measured in what unit? That's pennies, right? So that's cents. So then I guess dollars would be 10 to the 17. Okay, 10 to the 17. What is, it's in the quadrillion range. Well, that's a good question. It's a good question. All right, so anyway, that's quadrillions of dollars in there on this one thing of pennies. There's some story, I forget where it came from, about like somebody who the king was so happy with, he decided to pay him whatever he wanted, and the guy said, well, just give me one. This is a long time ago, so wheat was like really important. So he's, you know, just give me one stalk of wheat on the first square of the chessboard, and 2 on the second, 4 on the third, 8 on the fourth, just this. And the king said, sure, no problem. But this is like more wheat than exists in the world. Anyway, okay, let's, wheat. Petcher, number 9. Okay, so if we let the series go forever, it turns out that we have another nifty formula. I'm not going to write down the proof. It's the same proof that we did before. You list it all out, then you multiply everything by the ratio x, and you subtract, and lots of stuff disappears. So I'll just say that this is the infinity formula in number 10. Sum of an infinite geometric series is S infinity is equal to a over 1 minus x. Again, I'll write the other formula here just so that you see the similarities. A over 1 minus x is just part of the finite version, okay? And the only time this infinite geometric series converges is if x is trapped between -1 and 1. You gotta have small numbers. So you gotta be multiplying by something small. If we just keep doubling the numbers and adding, then it's gonna get bigger and bigger and bigger, right? Quadrillions of dollars on our chessboard. But if you multiply by small numbers, anything between -1 and 1, then it turns out the series converges every time. But if you multiply by something bigger, there should be equals on both of these guys. Can you add that? Bigger than or equal to 1, less than or equal to -1, the series diverges in both of those cases. Yeah, so if it's equal to 1, so for example, if I tell you the first term in my series is 5, and the common multiplier is 1, what's the next term? 5. And 5. And if you do this forever, you're going to get to infinity, right? Which is this is what it means to diverge. If I had said the multiplier was -1, and what's the next second term? -5, and then times another -1 becomes +5, times another -1. And so if you just look at the partial sums, that's 5. Add those two, 0, 5, 0. What do you think about that sequence of numbers? It oscillates and it doesn't get closer to a single limit, so that also diverges. What's that? No, half the time it's going to be 5 and half the time it's going to be 0. Yeah, it's either one, but it doesn't hone in on any single number, so it diverges. Okay, so you're going to be using 2 formulas today. Go ahead and start the activities on the next page and raise a flag if I can help.